Give me the Kp expression for equilibrium. You can write it in that box, by the way, because in a sense that's what we're solving for, so we need an equation to solve.
Stick that in there.
All right, if your answer matches mine on the board, you can have a smiley face. So all equilibrium expressions are products, overreactants to the power of their coefficients. Okay? Questions on that skill we need to be able to have? Yes, Stephen? No, I just sometimes there's a lot of like number things going on, so I just put parentheses, but not required. Calder. Because the idea is we're saying, hey, we're measuring the pressure of these things. When we use brackets, we're saying we're measuring the molarity of them. So if it's a Kc, then they'd all be in brackets, because gases can have molarities too. And you wouldn't have the P. So, but the basic setup would still be the same. So, questions on this one? Once again, so this was our main objective from last time, of being able to just write the expression, because today we're going to solve them, but if you can't write it, then you have a hard time solving it. Yes, Leslie? That's okay for now. The way I knew I wanted a Kp is because now we're going to be solving for it. Okay? So follow along with me in the question, everybody. I want you to highlight some certain things with me. Okay? It tells us a mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium. The equilibrium mixture of gases was analyzed. I want you to underline this fact of that it told us we are at equilibrium. That is very important to know. Right? We're not before, right? But we are at equilibrium. Okay? And we find to have these pressures of H2, N2, and NH3. From these data, calculate the equilibrium constant, KEQ, for the reaction. Now, once again, I wrote KEQ is like the general phrase of saying an equilibrium constant. C and P signify like what variables you're using. So since they gave me ATM, I know I'm measuring in pressure, so that's why I wrote it as a KP. Technically, if you write it as a KC, like, and plug them in, you're going to get the same answer because it's the same setup, but that's kind of the difference. Okay? So since I know I'm at equilibrium, all I have to do is just take the values they gave me and plug them in to my fraction. Okay? Don't lose your powers when you plug things in. So we'd have 0.166 squared on top. Okay, we got our N2 value of 2.46. Okay, and then let me pick one more color here. Okay, we got our hydrogen value, 7.38, and that one would need to be cubed. So we're just taking, once again, notice my colors, we're just taking the numbers they gave me, plugging them in. Let the calculator do the heavy lifting, and I got 2.79 times 10 to the negative fifth when I plug that into my calculator. Questions on my setup or any of my values? Yeah, Ray. Oh, great question. How is my face, Ray? You don't. Guess what? K has no units. It's unitless.
Yes. That's so good.
Which is nice, because I know that's often a stress for people. But now here's the bigger question of why. Why does K not have units? Part of it, keep going, Matthew. So it's a constant. Now keep in mind it's a tricky constant because it does change with temperature and it does change with each reaction. So each reaction has its own constant. But for this reaction at 472, it will always be this set number. Now let's dive a little deeper. I have a smiley face, Matthew, to what Matthew's saying though. Why though is there no unit with this constant? Because other constants do have units. Uh-huh. And the numbers we're using have units, right? So we're using unit numbers. Why does the N thing just not have a unit? Gavin?
Is it because K's units can also change sometimes?
Good thought. And that's the tricky part. In unit 5, we had a different K. That's different than this K. The only difference is that K was lowercase, and those units do change. This K is uppercase. But they're two totally different things, which I know is a lovely thing to keep straight. But not a bad thought, Gavin. That's my face. Marilyn.
So is it just that like all the units end up canceling out somehow? Or like, I don't know.
No.
What's the favorite representation?
There's the question we need to ask. It's because of what it represents. What does K tell us?
It says the equilibrium, it's just the ratio between the reactants and products.
Yes, it's a ratio. It's just telling us for every product how many reactants there are, right? And so it doesn't represent a measurement of things. It's just a ratio. So that's why it has no units attached to it because of what it represents. Okay? So let's decode what this number is telling us. So if this is my answer, what is this answer telling me about my equilibrium ratio? Right? Imagine we have our test tubes. Remember our test tubes last time? We had A and B in the straw game. Nod your head. Do you remember that? Okay. What would this tell us once we reach equilibrium? If this is my ratio, which test tube has more water in it? A or B at equilibrium, or the reactants or the products? What do you think, Stephen?
Did you ever have the high, like your times ratio about whichever had the higher value in that case?
That's what I'm saying. We did the math. Let's say we did the math of it. What does this tell me about the water levels? Do I have more reactants or do I have more products? Say it louder, Mason. This is what we call a reactant favored equilibrium.
As it becomes more product favored as soon as it approaches like 0.5.
Ooh, close. What would be an equal? What am I going to get if these are equal?
Oh, 1.
There you go. So 1 is the middle point. So anything less than 1 means you have more reactants because the denominator is bigger. Anything bigger than 1 means you had more products, and so it would be called a product favored equilibrium. Mary, then Stephen.
So, why would there be like reactants left over after the reaction has already like gone through all the way?
So remember with equilibrium is a dynamic system and it never stops. So that straw game is always going. The catch is it just gets to a point where the ratio doesn't change, but they're always reacting back and forth.
Oh,
Does that make sense? So it's kind of different because with other reactions that are not at equilibrium, we do say, oh, that reaction went to completion, right? All the reactants turn to product, but in equilibrium, it's just constantly going back and forth.
But if it's always going back and forth, then like why would you say it's reactant favored if both are reactants and both are products?
Oh, I see what you're saying. So in terms of terminology, whatever's on the left is termed the reactants. Whatever's on the right is a product, even though it's going both directions.
But if you flipped it over, it's just the exact same thing. It's just why it's written.
Yep, so however the equation is written is how you designate, okay, we're going to call these the reactants, we're going to call these the products. Does that clarify what you're asking? I know it's a little weird when you're going back and forth of like, wait, what one is the product and which one is the reactant? So, Stephen, do you have a question?
So if it's higher than 1, then it's the reactants are greater? Is that what you said?
Flip that.
Okay.
So reactant favored means I have more reactants than I do product, which is why my value, because this is less than 1, and since it's on the bottom of the fraction. So, did I see another hand? Yeah, Eddie.
So more reactants than products, is that more pressure, like more volume of reactants, or like more heat within the reactants?
More amount of them. So it's kind of interesting because we're measuring in pressure, but remember pressure is a direct relationship to molar ratios. So like moles and pressure are directly related. So it's actually like by the amount. That in our equilibrium system, we have a lot more reactants at that equilibrium than we do products.
Because the products. Okay.
Does that kind of make sense? Another way you could think about it, so like we have our equilibrium arrow, right, that goes both ways. If you want to draw this in, sometimes when I think of a reactant favored, is I think of it as the back arrow is a lot stronger than the forward arrow. So it's going both ways, but since it's going backwards a lot stronger, you get a lot more reactants made. But yeah, Miriam.
If it's just a ratio, then how like would it change with temperature? Do you end up with like a different ratio when it's hotter and colder?
Yeah, we'll get into it a little bit in a few days, but the idea is because if a reaction is endo or exothermic, that can drive it in one direction more than the other. And so it can push the forward reaction faster, causing it to be a different ratio.
What? But if you have the exact same like pressure numbers and then you just change the temperature one, like in this problem, if we change the 472 Celsius,
Then the pressure values wouldn't be the same thing.
all right.
Yeah,
Then
those would be something different.
If we manage to get them to the same pressure though, with a different temperature, then we still just have the same K.
It'd be impossible. Because you can't have the same K at different temperatures.
What about press, like hydraulic presses and stuff? I don't know.
Like what?
Sure, it's not possible.
Yeah, I'm like 99.
The same pressure,
It would be like
then
you
K
manage
would
to
also
like
change
push
with.
it down and then have it.
Because if you, like, they will change as you pressurize them, right? If you pressurize the system, you're going to make them react a certain way, which changes what they are. So, yeah, but not a bad thought. Hi,
Is there a Marissa Harris in this class?
Marissa.
Marissa.
Oh, she's my TA. She's over here. Yeah,
Okay,
she's
sorry,
just
this
over
is just for yearbook.
You're
Sorry.
good.
Yeah, she got voted for like the senior super lights.
Brissa, you get a picture taken for the yearbook. I don't know. They're here to take your
You
picture.
got, what'd you get? Most likely to win a staring contest.
Okay. All right. Try this problem. Notice though there's a typo. There's a 2 in that table. That 2's not supposed to be there. Scribble it away like mine scribbled away. Okay. I'll give you 2 minutes for a smiley face. Find me the KP value. Ready, set, go.
Two here, we also have to get rid of this one.
No, it's part of the balanced equation,
But
this is just the amount for just H2.
okay,
Does that make sense? Last period, people were like, is that the amount for 2 H2s?
it's just the amount.
But
for
it's just
one
the amount of
H2.
1 H2. But the balanced equation does stay, Gavin. But good observation. Yes, Henry? Okay, let's look here. So those, and that should be squared. And then this is just one thing, right?
I assumed it wasn't squared because
Oh, that's what, you just missed what I said. That was a typo. So scribble that too, so square it, and then you should be there.
Wait, is it the products?
Sabotage.
does it matter if it's a product or reactant?
Yes.
Wait, is it?
So it's always products on top, reactants on the bottom.
Yeah.
What if it says both?
Doesn't that mean
So-
they're both products and both reactants?
Yep, so by default, the left is always the reactant, the right are always the products.
Thank you.
Does that make sense? I know, equilibrium's a little confusing of like, who's reacting, who's producing?
What's the number?
Good job, have a smiley face. Ella, how are you doing? I know you were gone last time. But...
I looked over.
Oh, okay, perfect. And luckily it wasn't like, even if it wasn't too much, so.
Wait, was that a typo?
Yes, good
Wait,
job.
do we have to square it here? Because
Yes.
Okay, yeah, we do. But it's a typo.
Yeah, you just missed.
Yeah.
I know, confusing typos.
Bye.
Maybe by my 20th year of teaching, I won't have typos.
So do cross it out. You do square.
That's the answer we want, Henry. Good job. Have a smiley face.
So on the free response questions, it was like 0.500 times 0.005. So I think just 1 sig fig was right? Because my answer was like 0.003.
It's the original. So you got to go off for sig figs. You go off the original data. So the original data was 5.00 milliliters, and then you had to convert it into liters. So 5.00 has 3 sig
But
figs.
what was the 0.005?
That was it.
That's what you convert it to liters.
Sorry, I'm on her side now.
Does that make sense?
I'm on her side.
I know zeros are, well, it's tricky too because when you do work, you often don't keep the extra zeros.
What did KP equal? You weren't even.
All right, if you got an answer of rounded for sig figs 110, but if you got 109, you can still have a smiley face because you're on the right track. Questions on this one? Have a second smiley face if you identified that it was product favor for a bonus. Okay.
I'm so confused. I'm having a hard time visualizing what does 110 mean for equilibrium.
So it's saying like the ratio of product to reactants. So when I get to equilibrium, is you have 110 products for every one reactant.
For equal.
At equilibrium, yeah.
What's the difference between product and the other rate?
Product is just what's on the right.
I mean the product favored.
Oh, so that just means you have more products. Where for this one was reactant favored, so it means you have more reactants. So I'll show a video in a second, Michael. It might help a little bit. It might, yeah, because you'll understand a little bit more like what equilibrium is. But, so. Okay, next piece here, everybody.
Instagram Reels is like 2 schools in into the dies.
Same objective.
It's true.
We're still in 7.4. We're still finding the value of K, but we need to recognize that the process is changing. So I'm going to read it. Don't say anything out loud, but I want you to see if you can identify why is this problem. Oh, by the way, skip that question. Turn to page 4.
Oh, okay.
Sorry, I made a consecutive idea this morning to change the order.
Doing that problem.
Sorry, everyone there. Top of page 4. Okay, as I read this question, see if you can identify why it is different from what we just did. The goal is the same, but because of what's given, our process has to be different, okay? Don't say it, but just see if you can share after, okay? It says, for the given equation, initially the vessel is charged to 1,000 Kelvin with SO3 at a partial pressure of 0.5. At equilibrium, the SO3 partial pressure is 0.2. Calculate the value of Kp. So our goal is still the same, right? We're still trying to find our Kp expression, which is still going to be products over reactants. But by raise a hand, can you tell me why this is different from what we just did? Mason, what do you notice?
It's not at equilibrium yet, so you have to find where it is at.
Yes, right? We have one value at equilibrium, but we don't have the other values. Okay, does everyone see how that's different? Last time they told us all the values at equilibrium. If that's the case, bam, plug them in. If not, we have to figure out what those equilibrium values are based off what's given. AJ.
I assume that this also means that the total, that like there are no other like products already in the system when you start.
Good.
So we can calculate it with additional products in the system.
Yes. So what we're going to look at here is when you recognize there's a problem that doesn't give you your equilibrium values and you need them, you're going to think about rice. Rest, ice, compression, elevation. Just kidding. That's the physical therapy rice. This is a different rice, but it's still rice. Okay, well, R stands for reaction. I stands for the initial. C is the change. And E is for equilibrium. Thanks, Leslie. Okay. So rice is a problem-solving system to help you figure out, through initial conditions and a change, how much is going to be there at equilibrium. Okay, this is not my method. Like, I didn't make this up. This is I don't know how universally accepted, but if you YouTube it, you'll find it. Some people do just call it the ICE method and they don't put the R on it. I like to make sure we're referencing the balanced equation, so I like rice versus ice, but it's the same idea. Okay? All right, I'm going to use different colors for each step if you want to highlight with me to help recognize it. Okay? So the first thing you do with rice is, oh, that's not pink. Pink is going to be everything that was given to me in the problem. Okay, so start with what is given to me in the problem that I can put into my balance, into my chart here. AJ.
You know the partial pressure of SO3 before and at equilibrium.
Perfect. So we know initially it was 0.5, right? Did I read that right? Yep. And then at equilibrium, it became 0.2. Okay, so both those values just came from the balanced equation, from the given information. Stephen.
So since it's like before you get the reaction, there's a problem. So can we just put like our E in it? We'll be the price method. Like
The price. Oh, you want to make our own version and sell it for twice the cost? I like it. Price. Okay, now there's one other thing that is, I'd say, indirectly given, and AG pointed to it.
It also implies that at the starting pressure, we have no other reactions that we could not. We need to know our total pressure in order to.
So being that, what did they put into the flask?
SO3.
Just SO3, meaning no products have been made yet, right? So if they don't tell you they put products in, which they could, but if it's an equilibrium system and we only put in reactants, then there aren't going to be any products to start with. Just like when we did our activity last time, A was full and B was empty. Okay? So unless they tell you, the other ones will be 0. Yeah?
Does this also mean that 2SO2 plus O2 would be our remaining pressure, which would be 0.3?
So then our next steps I'm going to do in blue. Okay? So that is our directly given. And then what AJ is noticing here is that from our given, we can read between the lines. Okay? Okay, so we're going to read between lines of given. Because if I started with a pressure of 0.5 and I ended with a pressure of 0.2, then how much did it change by? 0.3. So we put minus 0.3 as our read in between the lines of the change. Does that make sense what I mean by read between the lines? Not directly given, but piece it together.
I can't remember the law that is assuming that the pressure is still the same, which has to be for an addition of pressures.
Did you see how
Pressures all add up, right?
Not entirely. But you're getting to kind of what we'll get to. So our third step here, can you read that green okay? Is that too bright for my third color? Okay. Our third step is to use the mole ratio to figure out the other changes. Okay, so use the mole ratio to complete the change. Once you have one thing on this C line, that's all you need, because the C is directly connected to the balanced equation. Okay, these are directly connected by having to have the same ratio. So, it's a 2 to 2 ratio. So if this changed by 0.3, then this one had to change by 0.3. The difference now is, though, it's being made, so we make it a plus 0.3. And see that? Then the O2 is a 2 to 1 ratio. So that means it had to change by 0.15. Once again, 2 to 1, 0.3, 0.3, 0.15. It's the same ratio. Questions on how I got those green numbers? So we're looking, so we knew this one, right? Does that make sense?
Yeah.
And so 2 to 2, so 0.3 to 0.3. That has to be the same ratio. And then a 2 to 1 means it's like half the amount. So 0.3, half of it would be 0.15. So you're matching these numbers, these 2, 2, and 1 in the balanced equation. We're just making it match the one we knew. And then, they're becoming positive because you cross the arrow line. So they're being made, not used up. Because minus means it's going away, plus means it's being created. Yeah, yep, you could. Any other questions on that? Yes?
So, does it matter that it's not actually just SO3, it's just a thing that it's just like a molecule that was reacting, so you add the same amount?
Yeah, because things react according to the balanced equation, right? So for every one of these that reacted, they're making one of those. The one thing that sometimes students get tripped up on is they think moles have to add up. So moles don't have to add up, right? Like this doesn't equal, like that doesn't, it could be true, but it doesn't have to be true. Mass is balanced, but moles across a balanced equation don't add up because we're breaking things, we're bonding things,
And also pressure.
and pressure, right, is changing based on those moles, right? Yeah, Mary.
Why did you get the 0 and 0?
Because in the first sentence here, it told me what did I put in my flask.
What's SO3?
So we only put this in there,
Yeah.
and so there wasn't any of this added. So that's why there's 0.
Wait, so initial is initial what?
Like initial conditions, what did I start with? So I started with this and none of these, and then it's getting to equilibrium. Kind of like, once again, we had only water in A in our test tubes, and then we swapped them, and then the water levels. Does that make sense? Okay. Yes, Stephen.
So if one of the zeros was a 1, like initial 1, and the equilibrium was 1.3, like you just add it together.
Okay, so now for KP, we got to plug them in, products over reactants, to our expression. So we have 0.3 and 0.15 on top, over 0.2, and don't lose your squareds. So that all the rice chart work was to find our equilibrium values. You guys remember rice charts?
Remember the word rice charts.
Well, let's see. I got an answer of, I don't, where'd it go? 0.3. How many units do I get here? 3? 338. Questions on rice charts before I have you try one?
Just send us into a deep end style.
Okay, before you dive in, everybody stand up. Some of you look a little drowsy, and it's not Mason for once. I couldn't resist. Okay, and then sit down and try, flip back to page 3, and try the one on page 3. The one with X's and Y's. Okay? Oh, sorry, but you just know me. There's another typo. There's 2 balanced equations, and they're not the same. The one that is correct is the one in the box. So, no, they're not.
Yeah.
No, oh, you go go back to page 3, Mason.
Oh, go back.
Back page 3. The one we skipped. Okay, good? All right, I'll give you 5 minutes, and then we'll check our answers. Are you guys done?
Oh yeah.
But like that one half hour? Oh, okay, let me come show you.
A lot of them are on
Were they supposed to remember these numbers? I know.
No, I just want my foot space. I'm taller than you, so I get my foot space bigger. It's not about the size of the dog, it's about the size of the fight. Say that again?
It's not about the size of the dog in the fight, it's about the size of the fight.
Did you make that? Did you make that, or did somebody else make that for you?
I made that.
Who made that? Who made that? Who made that? Who made it? Hey,
Guys, we're supposed to be working tomorrow.
liar, liar. All I remember is the one Kobe one. What was the one where it's like, be your own beast? Can you be the beast, but still be your own man or something like that? I'll find it. You have to learn it to be the beast while still being your own man. Right. R-I-C-E. What did you do? Oh, we don't even need to write it out. I haven't even heard much.
It's crazy.
And then they're allowed to react after.
Dang it, we have to
Yeah, we're supposed to write it out. I'm just listening to that paper, but they're saying that we have to write it out. Let's go.
None of this will be this.
No, we explaining to us how it last time. Yeah, which one's just too smart? Yeah. Wait, go on.
So like this thing.
C. E.
I still don't understand how any of these numbers came from except for the point.
They're allowed to react to constant temperature.
What does C stand for?
Are we racing it out? Are we not racing it out?
Don't listen to
This is where we should
Wait, what did Hadley say? Hadley, are we racing it out? Are we no race out? Oh, I was just saying the teachers okay, don't race it out.
Is -2 on the left or the right? It's right here, right? So then the other ones would be
That was a class-wide debate on whether or not we should race it out. We're not racing it out, right? We're racing it out?
very much.
She just said yes to both. I don't even know. What did you say yes to?
She said we're not.
Hadley, she said we're racing it out. We're racing it out. Why did I cross all this out? Okay.
So like notice when you build your rice chart, you have columns for each individual. So, do you see that? Like, this is for SO3, this is for SO2. So don't add your heat, your forward work together, just this and that. Oh, I think you might figure it out.
Exactly.
Go to your equilibrium and put your equilibrium.
Oh, so we end up with still the difference.
Wait.
Because you don't start with
That actually makes sense. Just like
oh, it makes that. No.
Don't press it. Don't press it.
why did you just not?
Stop.
What's your name?
That's Leslie. You can just think of her because she's lesser than me.
just gonna let her say that? Can't stand up for yourself, no self-application? Ooh, it's not a good strategy. She has no fight. The dog is fighting. Or the dog is full of dogs too. Yeah, it's a small dog. In the small the value of the equal cows, that is it? Wait, but Adley!
Almost there.
So close.
The reason why you split the it's like X, Y, Z. I mean, I would just write it as so in the beginning, you don't have any Z present, right?
Got it.
So what does this mean?
This is what I got.
These should be minus. They are being used. There you go. But this 90 milligrams, so that's not your change. I mean, it kind of is. 6 at the bottom.
Like half of that?
Oh, so I was on the right track. Oh, and then you have to put it in the
So now, I mean, it is still plus 6 there.
Rachel's wrong.
So then match the balanced equation to the change. If this is 6 and that's 2, then that should be. So a 2 to 1 ratio, 6 to.
Is it 6 over 1? Oh, it's 6.
So to go from, no, that's 0, right? Leave that 0 there. To go from 2 to 1, how is it changing?
Is it 36?
Keep that 6 there.
36 more.
So to go from 2 to 1, there's 2 Z's and 1 Y. What's the change from 2 to 1? Not addition wise, multiplication wise. There you go. So if it's 6, then Y would be. No, not there. Change. So the initial is the initial, but the change should match the balanced equation.
Wait, so am I right then? I got 36 more.
Oh, but no, you didn't.
36.
White. Now, the only difference is this is being made, and these are being used, so it should be minuses.
And he was like, okay, I can do the next page.
I might just go chat in the comments for a little while. We should go find Miles. Chatting in the comments is chill, but it's really chill. It's usually chill when I park over there and not over there. Because I usually park by the dance room.
Instead of a 2 here,
So last night I was doing a math review. I was doing the 68 problem math review, but I didn't even finish it. 4 hours on it. I would do like 6 problems and then spend like 20 minutes scrolling through TikTok. Or Instagram Reels, or whatever social media platform I'm doing. Like YouTube. There's a point I was on the new Xiaohong Shu app. Have you seen Chinese TikTok? Did you say Xiaohong Shu?
I'm mean to you just by like, he doesn't bring you more examples.
I don't know why Xiaohong Shu referencing it. And you, because now all the Americans are on Xiaohong Shu. It's Chinese TikTok. Yeah, it's Xiaohong Shu. Yes, the name of it.
so funny again.
The name of it is shell, which is little red. The direct translation is little red boat. Also, are you going to Chinese New Year? Wait, no. Most Chinese speakers hate you say that. You can say not hate, but like it's how is more like street style. Actually chill because Anderson's such a dope teacher. But it also sucks because if I took it like 5 years ago, if I were just 5 years older, I would have thought we used to get $10,000 from the Chinese school to learn Chinese and never fund their trips. So instead of spending $4,100 to go to Taiwan and Beijing, I would spend like $2,000 to go 3 weeks in China. That's crazy. But I'll still get to see the Great Wall this summer. Wrong wall.
No, you should see that instead.
A lot more horrifying of a wall. That was a wall meant to keep people out and not to protect the people inside. Oh. Yeah, that does suck though. Because it is so cheap to live in Taiwan. So, yeah, my sister. Yes, what'd you get? 36? That doesn't even look like a 36. That looks like a 7. A 7. I'm sorry. That was beautiful. As somebody earlier today said, Trump should take control of the Panama Canal with love. He should say, he should go to the Panama government and say, can we have your canal please? With love. No. We were talking about whether or not we should take over the Panama Canal and push today. English is such a cool class. Plus, the Chinese teacher is also the English teacher. So my third period is always an English class. I'm not sure, but
Do you see that a little bit, Michael?
Yeah, that's what I thought.
Okay.
There's, if you come to that day, get shirts, or you can buy shirts online. What is it?
Okay. I think we all got there. 36 gives you a smiley face. Any questions on using a rice chart?
World.
I feel like every time I teach this lesson, I want to have like some rice we can just like throw in the air after we solve a problem, right? Wouldn't that be fun?
He's like, what did you just say? I saw Nathan grab his thing.
Okay,
I disassociated first.
let's take a look at another way in which a rice chart can be used. So on tonight's homework for 7.4, okay, once again, you have now learned the skill of rice charts. The next step is learning how rice charts can be used in a variety of ways, because that's the AP test for you, right? Is they take a skill you know, but then it changes in the problem. But the skill doesn't change, okay? All right, I'm going to write my equation. I think you already have one written below. This is on page 4, by the way.
Dude,
we're back in order.
How is there ink on my pen from the ink of the pen? It's like reverse gravity.
Okay, see if you can recognize why this rice chart, there's a little twist to it, okay? It says, a pure sample of PCl5 is placed in a rigid container, evacuated 1 liter. Okay, the initial pressure is 1 atm, so I'm going to plug that in right now. So I know this is 1. Which also tells me I can assume the other 2 are 0, meaning I didn't start with them. Okay? The temperature is held constant until it reaches equilibrium. The total pressure in equilibrium is 1.4. What is the value for Kp? So what's different about this one from our last ones, Calder? it doesn't give us an individual equilibrium pressure. It tells us a total pressure. How does that fit into our chart? Any ideas?
It's all of these added together.
Good, Mason. It's this plus this is going to equal 1.4.
That's a lot of empty space.
It is a lot of empty spaces. And that's all we're given. Like, there's nothing else in the problem. So, when you find, look up here, everybody, that you have no information about individuals, like, if you don't have any of these, you can't directly figure out any of those. So what we're going to use is a variable, because we don't know what it is, but we know they're going to change. I know some amount of PCl5 has to go away, because it's making product, right? Some water has to go into B. And by the balanced equation, because it's 1 to 1 to 1, these are going to increase by that same ratio. Now, keep in mind, it's not there, but just to emphasize it, right? If there was a 2 here, then this would be 2x, right? But in our case, it's 1 to 1 to 1. Okay, I'm going to carry everything down, so we get 1 minus x is the value here. This one just equals x, and that one equals x, and we know what it equals. So we can solve for x. You can see that? So if I simplify this, we get 1 plus x equals 1.4, because the negative x and x can cancel. And x equals 0.4, and I circle it and move on.
Really?
No, I don't. Good.
Oh.
Sometimes students get so excited because they found x that they're like, I found x, I got the answer. But is that our answer we want?
No, bad answer.
What do I need to do with it?
Put it into the thing.
Yeah, we got to plug it in for KP. Okay, so we'd have 0.4, 0.4, and 0.6. And I don't remember what my answer is. Someone want to type it in for us? Oh yeah, that's right. It goes 2.26 repeated. Okay. So I think we get 3. No, we only get 2 sig figs. Beep, beep, beep. 0.27 is your answer. Yeah, Marilyn. Because the value of this one is 1 minus x. So x equaled 0.4. So 1 minus 0.4 gives me the 0.6. Does that make sense? Good question. Because this is the equilibrium value. So these are what we're plugging into here, right? Because you always plug in your equilibrium values. Does that make sense? And so we had to plug this in here to find its value. So 1 minus 0.4 gives you the 0.6. Does that make sense? These two just equaled x, so they could be plugged straight in. So. Okay, now, don't go x crazy. Okay, I show you this as an example because it's a way to solve certain race charts, but I find sometimes after I do it, then students try to do every problem by putting x's into it. And if you try to throw x's into this one, it's like gonna get so messy. So when do I need to use x's?
When you have no idea what the change is.
When you have no information of change or equilibrium, right? And they're gonna give you a total pressure to add it up to, okay? But keep in mind, like, I would say it's less likely to use x's than to use them. So just be aware of that, okay?
You said it's less likely to use x's than to use them.
So like, oh, that was confusing. What did I mean to say?
I don't even know.
It's less likely
I'm like double negating. It's less likely to use them. You're not, there you go. You could use them, but it's not likely.
Yes.
More often than not. That's a good way of saying it. Okay, last objective really quick here. We've already kind of touched on it, but let's put it in our notes, is what does K represent? So this fancy word magnitude just means numerical value. Okay, so what does the numerical value of K tell us? Okay, so as we mentioned, I'll come to these blanks in a second, but I want to focus on what we already hit. Okay, if K is bigger than 1, then we indicated that that means it's a product favored equilibrium. Okay, you have more products than reactants. If we were to graph them, we would see our product line would be on top and the reactant line would be on the bottom, possibly really low depending on how product favored it is. Okay, if K is really small, then that's what we call reactant favored. And obviously vice versa. Okay, so when you are given, so obviously we practice finding K, but there can be times where a problem gives you K. As soon as you see a KC equals or KP equals, your brain should stop and interpret, what is that telling me? I do the same thing anytime I see a delta H. If a problem gives me a delta H, before I even read the rest of the question, I make a quick note, oh, that's exothermic. Right, so I have that knowledge going into the question of, they've given me this number and it's telling me information. Okay, what is it given to me? Okay, our blanks that I don't know where went are equilibrium, constant. No, wait, that's not equilibrium. Hold on, I backed up. The value of the constant. Okay, so the value of the constant provides us important information about the composition of the mixture. Okay, as we've noted, it's always products on top and reactants on the bottom. Which is why, if it is going to be a very big number, then that means the, do you want to say it in the math way or non-math way? The top of the fraction, also known as the numerator, okay, must be much larger than the bottom of the fraction or the denominator. Okay, so think of just the biggest thing is remembering, and technically once again, K is on your formula sheet. You don't even have to remember that it's products over reactants to the powers. It's actually there for you if you forget, but I don't know why compared to other things I wish were on there. Okay, let's try one problem really quick with interpreting this, okay? So it tells us we have this reaction and it varies with temperature as follows. We have a K that's 794 at 298 and a K that's 54 when it goes to 700. Our question is the formation of HI favored more at a higher or lower temperature? So here's Miss Alviso. I'm talking through you what my brain says to myself. Okay, because that's how you solve problems, is you talk to yourself. Okay, so my first thing my brain says, okay, well, I want to favor HI. So is HI a product or is it a reactant? Good, so it's a product. So I'm going to mention that to myself, right? Okay, I'm trying to favor product formation. Okay, the next thing my brain says, okay, well, what did it give me? It said K is 794 at that temperature of 298 Kelvin. Sorry, there's a lot of K's with K's and Kelvin in here. What does a 794 K tell you about an equilibrium? Good, so I'm going to label this is product favored. All right, the other temperature told me the K was 54 and our temperature is 700 Kelvin. So what is 54 in relation to the one we just wrote? Also, but less, right? So I'm going to say it's less product favored because I'm trying to compare them. All right, so once again, I'm just taking the information they give me and I'm interpreting what is it telling me. The question says, is the formation of HI favored more at higher or lower temperatures? And from the data, we wanted lower. So it seems like for this equilibrium, the colder it gets, the more products that are made. Is that questions on that? Okay, oh, good timing, low battery.